So these are two greenhouse-like clear polycarbonate multi-wall sheets. On the right is an off-the-shelf 6mm thick twin wall, one air gap, and on the left is a custom sheet from Tandem Polycarbonate that is still 6mm thick, but it's 4 walls and 3 air gaps. Each air gap is roughly 2mm apiece. I'm going to be using these in a series of thermal transfer tests. So in addition to those two OEM sizes that I got, I also wanted to experiment with some thinner variations. I tried to use a handsaw, but it's only 2mm, hard to keep straight, so I got a little bit on the outside. I ended up switching to a DA and sanding it off. And I ended up sanding it down and got down to a 4mm thick, 3 wall, 2 air gaps. And then I also, with some more sanding, got it down to 2mm thick of 1 air gap, 2 walls. And we'll see how they do. So altogether, it was about 100 hours to assemble, prep, test, collect all the data and so forth. Thankfully, it wasn't all active time. I could set up a test, let it log, come back, set up the next one, let it log, so there's for 10-15 minutes in an interval, and then use a spreadsheet to crunch a lot of the data. So that was useful because I have a day job and it's not the only thing I do. But you're going to benefit from taking all of that into some graphs and some commentary in just a few minutes. Now, depending upon an application, you may design specifically to take advantage of different properties. For instance, a heat recovery ventilator might deliberately want to transfer heat from one airstream to the other. Or say, for instance, if you're doing glazing, windows on a house, greenhouse, or say a solar thermal collector, you might deliberately want to cap off, prevent airflow in that channel, so try to retain as much heat as possible from, say, front to back of the panel. Or say if I'm using this, say, under solar panels on my car, maybe I want to have some airflow in there to cool that heated solar panel surface, or cool the opposite of that heated surface, say the car, by transferring some of the heat into the airstream, depending on the application. So let's take a look at how some of those tests turn out. So first, let's take a look at probably the most common type of application for these multi-wall panels, and that's in greenhouses, where you would cap off, or something like that, where you cap off the ends and they're not having any airflow. It is clear, so light can get through, solar thermal heater and things like that, but you want some insulating value, some temperature difference. You will sometimes see it advertised as an R value. In this case, I just have so many degrees of Fahrenheit temperature difference. We also compare it at the top to mineral wool, 1 inch, and 1 inch of foam board, which is R6. So you can see how the difference here, that 1 inch is 25.4 millimeters, so the 4 of the 6 millimeters at 24 millimeters is almost up in that 1 inch, but it doesn't insulate as well. It is clear, so sun can get in, but it doesn't insulate as well. We can also see in this that the 4 wall thick is doing slightly better as a thermal, even though, so in 1 6mm of each, the 4 walls thick is slightly better, and then in 2 thick or 12mm, it's slightly better. So in each case, you can see how having those extra walls, even though the overall is still the same distance, 6mm, 12mm, 18mm, or 24mm, the additional walls actually help improve the thermal insulation, slow down the thermal conductivity through that medium. And we can see even the smaller 4mm and 2mm do still significantly reduce the amount of heat transfer from face to back. Now, if they're not capped, if instead there's some airflow, and you can see here there's a small amount of airflow, we're talking 1 or 2 miles per hour of airflow, it's not a lot of air, but if there's some airflow movement, then that air that travels through will carry some of the heat away. That's one of the reasons you cap it if you're trying to insulate. But if you're trying to transfer heat, like say in a heat recovery ventilator, or you're trying to remove heat by putting it under a solar panel in your car, then that application could be useful. And in this case, the non-vapor permeable things like the foam and the rock wool, they're not letting air get through, so they can't benefit from that. But even small amounts of air movement, we see the delta T get very small. And the reason for that is that a lot of the heat is now going into the air that's transferring through, instead of those two surfaces being hotter, or either outside or inside. And we'll take a closer look at that. And the first part of that we're going to take a look at is on the surface opposite the heat source with air running through it. You can see here the massive differences that you have if you do, say, nothing versus you have insulation, and then you have an airflow. Once you have an airflow going through, the temperature of that other surface opposite the heat source is massively reduced. A lot of the heat is transferred off. Which can benefit if we're thinking of, say, in a car application, then that would be if the heat source is the hot solar panel, then this is reducing the amount of heat that gets through to the car roof itself. And here we see that exterior, the side opposite the heat source, if those air gap spaces were capped off and there's no airflow, and you can see a massive difference in the amount of delta T, because now it's no longer transferring it to the air, and instead it's acting more as just a regular conventional insulating material. The air isn't taking the heat away because the air isn't moving in it. And here we can see the interior, or on the heated surface itself, with a small volume of fan air movement, the massive difference where if you have that foam or insulation above it, that heated surface gets insulated. It holds in all of its heat. You see it at the top. But with a little bit of airflow, you can see on those multi-wall polycarbonate panels, 2, 4, 6 millimeters, just a little bit, and you can have a massive reduction, cooling of that heated surface. If that's what you're trying to do in like a heat recovery ventilator, or on the car, if I'm trying to cool the panel, I want that airflow underneath of it to help cool it. And here we take a look at, if we're looking at on the heated surface itself, where that heat is, let's say the solar panel or whatever, if it's capped off, if that air is not moving, and we see a significant difference again, because now without air moving, those dead air spaces are mainly just acting as a thermal insulation. They're not, wicking away and transferring it into the air. And so again, now in this application, because there's not air movement flowing through, then there's less conductivity. So of course the smaller, thinner one has a smaller temperature because it doesn't insulate as well, and it can wick off more of it from that heated surface. Now, if you're trying to be under the heated surface, then you would want, we're going to go back to, airflow if we want to cool that surface. And if we want to keep our heat inside, then that's a different property than trying to cool that exterior surface. Just a few other quick notes and observations. One is that all of these had the same amount of watts of heat being applied in the same surface area, so that part's interesting. And the fan had the same amount of watts of power being applied. So it's interesting to see the different speed of air that was measured coming out at the different air gaps of 2 millimeters or 4 millimeters, and the difference between, say, 6 millimeters, just that's twin wall, versus 6 millimeters, that's 3 wall. So there's some differences there in airflow. Part of it's because the obstructions, and if you have a restriction in airflow because it's small space like 2 millimeters, then that's going to restrict. So even if you might be trying to push it in, you're not going to get as much through because it's obstructed and it's restricted airflow. But it's interesting because as it gets bigger, the speed increases some, but it's also interesting to note that you're also vastly increasing the volume. To go from 2 millimeters to 4 millimeters, it's twice the height of that air channel. So even if it were the same speed, it would be twice the volume, but actually the volume goes up because there's less restriction. And by the time you get to 6, you're 3 times the volume of air, but you're moving, even if it were the same speed, it would be more volume of air. But because there's less restriction, it also travels faster, which further increases the amount of volume of airflow, which is an interesting note there as well. And of course, multi-wall polycarbonate sheets are not the only way to get an airspace under a solar panel. If it's mounted, a solar panel has a racking system mounted on your home, you probably have an airspace that's ventilating under it. If there's a racking system on top of an RV, like a luggage rack kind of mounted system, there's probably air gap and it's ventilated that way. So yes, there's a lot of other ways to do that. And if you have no air gap and the solar panel is just directly adhered, and I've done that and some other people have done it, it's not that it doesn't work, it can work. You just don't have that cooling effect. You don't have the separation to help reduce some of the heat getting into the car, and you don't have some of the heat reduction of the panel itself. I was potentially looking into this particular direction because my 2000 Gen 1 Insight that I have solar panels on now, and I have a slightly improved upgrade that I'm going to be doing to it, I'd like to have a little bit of an air gap under there to reduce some of the heat getting in the car. Might be nice to help reduce the temperature of the solar panels a little. Might be nice for their longevity, for their efficiency, and so forth. But because I want to try to retain a good bit of the aerodynamic profile of my car, so I didn't want to add like a luggage rack or something that would create more obstructions, increase the frontal area, and reduce my wind resistant CD, coefficient of drag. So I'd like to keep my wind resistance penalty for the solar in my car down to a minimum. So the twin wall was kind of appealing to me that way, in that I might only need 2 millimeters to get a little bit of airflow under it, or only 4 millimeters. You know what I mean? So I can have a fairly small space under it that's still conforming to the shape of the curvature, and still get some cooling effect under it without getting bulky and things like that. And I can even on the leading edge still have an angle and curve. At least that's the thought.